So I think in the class notes, I talk about how industrially water is added to ethylene with phosphoric acid. So let's add a little lone pairs here. And the temperature is quite high. And so we end up making ethanol through adding water across the double bond here. Very high temperature. And this is basically a source of acid, right? Phosphoric acid. So you could have, you could draw a mechanism for this where you've got your double bond attacking, generate your carbocation. Water comes in and attacks. And we will use let's use the anion of phosphoric acid to deprotonate your structure here. And voila, we have made isopropyl alcohol. Okay, now one of the things you'll notice here is that if I start with propene and I do this reaction with phosphoric acid and water and we heat it up and we make isopropanol, you'll notice that we make isopropanol and not propanol. So we wouldn't be making this. And the answer, why do we not make this? What's the key factor for not making that? Why wouldn't we make that? Right. So the first step, this mechanism is exactly the same as if we had if we'd started with say HBr. We need to make the most stable carbocation. So in this case, it's a secondary carbocation versus this one would have to come from a primary carbocation, which would be too high in energy. So using a strong acid, or it's like phosphoric acid in the presence of water to do this reaction is going to give the Markovnikov product, right? The rich get richer, and the OH group is always going to go on the more substituted carbon. Now, the trouble with this type of reaction, there's really two problems. The first one is you're using a strong acid, and if you've got a complex molecule, it's probably going to, strong acid's probably going to chew it up or destroy it because there's going to be other functional groups that are sensitive to acid. The second problem, of course, is that you're heating this up to really high temperature. So this works industrially fine. Like they use it for the synthesis of ethanol. And they probably use it for the synthesis of isopropanol too, although there's other ways to make isopropanol industrially as a side product of a different reaction. But anyway, it's not particularly, the take-home message is that this isn't particularly useful in the lab for what we are trying to do, because we don't want to heat something to 200 degrees and we don't want to throw a really strong acid in there, particularly if you've got other functional groups. So chemists have developed two other ways of adding water, which don't involve high temperatures and don't involve strong acids. Addition of water. And we want to be able to make, if you have, say, propene, we want to be able to make, say, isopropanol, and we also want a method which can make propanol. So we want basically two types of methods. So one where we've got the Markovnikov, this would be the Markovnikov, and the other one which would be the anti-Markovnikov. So one where the rich get richer and one when the rich don't get richer. So let's do, we'll call this one here route A. We'll do this one first because what we're going to see is that it's very similar to what we've seen before. So route A. And this is what we call an oxymercuration reaction. So we're going to be using mercury. And so I'll just draw say the reagents that we use. So this is going to be a two-step process. So it's two reactions, one sequentially after the other. The first one is going to use mercury acetate in the presence of water. And I think the other typical solvent that they use would be THF. The second step is a reduction with sodium borohydride. And our final product is going to look like this. So the H gets added to the the least substituted carbon, so the rich get richer, and the OH gets added to the more substituted carbon. So this is Markovnikov. Okay, but let's do the mechanism first. So mercury acetate. So remember, the acetate group is this. So this little squiggly line is whatever it's bonded to. So the OAC, it's basically a carbonyl plus a methyl group. So mercury acetate would look like this. There's another reagent which has been used, which I remember using when I was doing grad school, which was this version of it. And this is might help. This version is slightly more reactive, and basically it's the same thing except for there's fluorines on the acetate, which we would know which would be electron withdrawing inductive effect. So this mercury here is, and this is going to be our electrophile. So remember last term we talked about transition metals and that type of thing. So this is going to be our electrophile. So the first step is that, okay, so what can you tell me about this, the acetate, the carboxylate anion here? We saw this a little bit when we were doing substitution reactions. Okay, let me ask this another way. Would you, if you had to classify this as a acid or a base, you would classify this as a base. Okay, good. And then the next question is, would it be a strong base or would it be a weak base? Weak base. Okay, and why would it be a weak base? You're correct. Okay, so this negative charge is stabilized by resonance, right? Okay, so it's a weak base. Negative charge is stabilized by resonance. So weak bases made good leaving groups, right? So that was one of the things. So this is actually, this little part of it is a leaving group. So what we're going to do is we are going to have our alkene, because remember, this is going to be our nucleophile. It is going to attack the mercury, and one of our acetates is going to leave. And so this is going to, actually, let's do this the other way. So the first step is this. Okay, now, okay, so this is what I purposely drew this carbocation on the more substituted carbon, right? So this is tertiary carbocation. Now, mercury is a transition metal, so it makes sense that this is it's an electrophile in this sort of case. Mercury, if you look at the periodic table, Mercury is towards the end of it's in the final column of the D block. So Mercury has got some electrons. I'm going to draw two of them here just because, but it has got some electrons that it can use. So my next question is, what do you think happens next? And of course, we've got some water here in the reaction. There is a very similar effect from the bromonium ion. So what happens next is that, so we could have, because what we need to do is we need to have our OH group come and attack the most substituted carbon. But as I said last class, who can touch your feet faster, you or somebody else? So the first thing which actually happens is that the mercury can come in and make a three-membered ring sort of structure that looks like this. Try to draw that as best I can. OAC. Okay, and then mercury is going to now have a positive charge. And so this is what we call the mercurium ion. I might have spelled that wrong. I'll have to look that up. And this is exactly, it is basically completely analogous to the bromonium ion. So this is why I always do this one next, because it behaves exactly the same as the bromonium ion. And so when water finally attacks, it's going to, the philosophy of this is it's going to attack exactly the same way water attacked the bromonium ion. It's going to attack on the more substituted carbon, and it's going to be on the opposite side. So what we'll have here, we'll use the purple thing again. This will attack the more substituted carbon. So it's SN1-like and it's SN2-like. It's SN1-like in the sense that it's attacking the more substituted carbon, but it's SN2-like in the fact that it's attacking from the opposite side. So there's some, remember this carbon, this bond here, which, this little bond here, it's weaker than a normal bond. So this positive charge is technically shared amongst the mercury, and the two carbons, but the carbon here, that bond is the weakest for, because it can better stabilize that partial positive charge. So when this attacks, we end up with a structure that looks like this. So we'll get inversion at that. So this methyl is going to be forward. The OH is going to be backward, opposite side, and the mercury is going to be there. So we still have to deprotonate that last little proton here. And to do that, let's use our OAC. It's a pretty weak base. So let's deprotonate that. You could use water as well. And this will give us our final, this will give us the product after step 1. So after step 1, Hg, OAC, and then methyl OH. So these two groups are anti. And the OH is on the more substituted carbon, which makes it a Markovnikov addition here. So Now, the final thing, the final product, we need to, the second step here is the sodium borohydride. So, so this is a source of hydride, which is H negative, right? So sodium borohydride. And after we do this, the reaction is I'm going to draw this mechanism in the following way. It's not the, you can just think of this as sort of that H minus attacks the carbon and the mercury leaves with, but it's an oversimplified version of it, but for what we're trying to do, that's good enough. And that will give us our final product. So the interesting part for this, so if we want to do this oxymercuration, yeah, it requires 2 steps. So the first step is using the mercury diacetate in water and THF, and the second step is the reduction using sodium borohydride. For me, if I'm asking this question on a test or something, the more interesting question is this one here. Okay, so let's do an example. So let's pretend that we've got or let's do this reaction. Okay, so in scenario 1, we do a Markovnikov addition. So we do the oxymercuration, and then we reduce off the sodium borohydride. So we're adding H2O across a double bond, and the rich get richer. So the carbon, which has got the proton, is going to get the proton. So our final product here, or our final answer, would be this. Because these are both methyl groups, so it's 2 methyl groups. So that's what this would look like. What's far more interesting to do is to leave off the second step, because in that case, the product, if we're drawing this, actually, I should probably make that an ethyl group there. And you'll see why this is the correct answer would be this, or it would be this. So you have to have the OH to the more substituted carbon, and then without you have to have the methyl group and the hydroxyl group, sorry, the the mercury substituent and the hydroxyl group on opposite sides. So asking scenario 2 question is far more interesting because there's other things going on, right? So so to actually do the oxymercuration, the second step, you need to have the sodium borohydride to make what we're trying to do. But when it comes to, quizzes and questions like this, the second, you can see that this one's far more interesting because there's more things going on, right? So just keep that in mind. Is the sodium borohydride there or is it not? So the sodium borohydride is used to remove the mercury. So just keep that in mind. Is there any questions on the oxymercuration? It's very similar to the bromination, the halohadron reaction, where you've got bromine, your electrophile, plus water, the nucleophile in the second step. It's almost completely analogous. The only thing we need to worry about is getting rid of that mercury in the second step with the sodium borohydride. Okay, sure. Let's do okay, let's do an example. Okay, so we had, so if we had this and we are going to do the oxymercuration, so if we're going to do this, I could draw this, or I could draw this. Which arrow would be the first arrow that I want to draw? The orange arrow or the green arrow? Green. Okay, so if we draw the green arrow, our intermediate is going to look like this. HGOAC, positive charge, OAC minus. Right. So we would put the positive charge on the more substituted carbon, right? So it's looping, the green arrow is looping towards the carbon on the end. So that means the positive charge will be on the middle, right? So the second step is we are going to form our our mercurium Hg positive. Now in this question here, because it's a terminal double bond, the stereochemistry isn't nearly as important because there's no substituents on the end carbon. So our next step is going to be water's going to come in and attack. And so if this is forward, let's draw two arrows here. I could draw this arrow. So it's coming in from the opposite side, or I could draw this blue arrow where it's coming in on the same side as the mercury. Which arrow would be correct there? Orange, right. It needs to attack from the opposite side. So so with this one, we would have OH. But the trouble is with the mercury on the end, it's going to look like this. Next thing would be that the O acetate minus is going to come in and attack there, grab that proton. So it'll be deprotonated. OH. And then the last step would be sodium borohydride is going to come in and reduce this. Now, what I've drawn here, I've drawn this OH being in the background because of the way I drew this mercurium ion here. My question is, should we have one enantiomer as our final product, or should we have both enantiomers? Should we only make this, or should we actually have both of them? I've got one person saying both, two people. Right, so the correct answer is we should have both enantiomers. I could have, during this first attack of the double bond on the mercury, I drew this up just because there's nothing stopping us from having this mercurium ion formed as well. And if I had this mercurium ion, because that double bond's flat, right? So the mercury can be attacked from the top or the bottom. So you could get both of these. Both of these mercurium ions would be formed. And if I had this other one in blue and I had the water attack it, in that case, it would have to come from the top. And then that would generate the other alcohol, which would eventually get deprotonated and you would form. So you should actually get both enantiomers out of this. We'll see a bit later that there are ways to make one enantiomer over another, but not with this reaction working this way. You would have to do something. Let me think about this. If you wanted to do this, you would have to actually make your leaving groups chiral in some way to make that work. Or have a chiral catalyst that facilitated the reaction. But for what we're dealing with this mercury, dimercury acetate, you wouldn't get that. So you'd actually make both enantiomers. So if you've got a terminal double bond, you're going to end up making the secondary alcohol. If you have a double bond that is, actually, let's change this just a little bit. Then in this case, we would have, you're going to put the hydroxyl group on the more substituted carbon. So that's basically the oxymercuration reaction. Now there's a, there is a complementary reaction, which is what we'll do next. So key point, when you're adding OH across this, these are Markovnikov. So the OH is on the more substituted carbon. Right, the complementary reaction is root B. So now let's go back. So with root B, now we're going to find out how to put the OH group on the on the less substituted carbon. And the fun thing is that we're going to use another element. So we got to use mercury here for the first time. We're going to use another element, which we've seen before. And so you should be able to tell me some stuff about it. And this is what we call a hydroboration. So we are going to use borane, which the way that organic chemists organic chemists draw this. They draw it like this. And why do they draw it like this? So this would be looking from above, looking. And this would be looking sideways. Right, we draw it like this because to show that it is trigonal planar, which means it has got this empty orbital, which means that it is what kind of reagent, if we were to loosely categorize it? Is it a Lewis acid or is it a Lewis base? Right, it's a Lewis acid. So it's got this empty orbital. So therefore it's a Lewis acid. And which means that the double bond is going to attack it, which is what we want to see. Now, if you talk to an inorganic chemist, they would basically minorly freak out if we drew this in this fashion, because they would say, wait a second, that's total nonsense. If you've got borane and it's by itself, it's actually tetrahedral and it looks like this. And actually, I'll draw this with a different color. They say it's tetrahedral, and these two hydrogens in the middle, they basically share their electrons with both borons, and they basically form a dimer. And these bridging hydrogens, these because the way that we draw bonds, remember, it's got two electrons in it. And they're basically saying that this isn't a full bond, it's actually shared bond. This is a shared bond. And they're sharing their electrons. Yeah, but that doesn't help us do, that might be completely true, but that doesn't help us describe its chemistry, right? So it's better, this is why we draw it like this. So borane, when you buy borane, it's typically sold in a bottle of THF. And of course, THF looks like this. And so THF would be a Lewis base. And so these lone pairs would be donated into this orbital. So it's a complex of BH3 plus THF when it's being sold. But if we want to think about it how it's reactive, we would think about it as I've circled in this little blue circle. Okay, so if we've got a double bond and we've got BH3, the way that this works is that the p orbitals of this, let's see here. I could actually draw this two ways. Let's draw it both ways. Okay, so I'm going to draw an attack of this double bond onto the empty orbital of boron. And I'm going to do the same thing over here, but I'm going to do it from the other carbon. And so if we were to just make this, I'll draw this as this is a formal step, and this is what it would look like. So the product of this reaction would look like this. And the product of the other reaction would look like this. So boron's now bonded to 4 things, so its formal charge will be negative. The carbons now have no electrons there, so now they have a positive charge. So if the reaction went through one of these two pathways, which one do you like better, A or B? And everyone is telling me A, and the reason why you like A better is because carbocation stability. Okay, good. So, right. So this would be the favored version of this. And then the second step, you could see immediately that, oh, I've got a negative charge here. So this hydride could immediately attack that proton, and then this would, or that carbon, and we would end up with this. So the way that this works, it isn't technically like a formal step where this is a discrete step and this is a discrete step. It's almost a concerted reaction in which, as the electrons are as these electrons are attacking here, this hydride would come and attack there. So it's almost a concerted reaction. But drawing it this way helps us visualize why the boron should end up on the least substituted carbon. Now, there's another reason that people have suggested, ignoring the carbocation stability. They would also say that sterically, if you have the boron on the least substituted carbon, there's less of a steric factor as well. But I think that's the better way to do it. Now, the second step in this reaction is, actually, before I do that, as you will notice, the boron has got 2 other hydrogen atoms attached to it. So theoretically, this could still react with another molecule of twice. So in the end, you would have something which looks like this. Is it pro 4? Sorry, 1, 2, 3, 4, right. You could have this we'll call it trialkyl borane. So stoichiometrically, if we're doing a reaction with borane, you can actually use less than one equivalent. You could use technically 0.33 equivalents of BH3 to do this reaction. Depending upon what your molecule was, how big it is, and all that sort of stuff. So it's an interesting thing. So you could make this trialkyl borane, and then that's the first step, is just using BH3 in, so the first step is using BH3 in THF. The second step is the one which is really, we need to convert the boron into the oxygen. So the second step is the oxidation reaction. So it's, what is used is, and this is usually just abbreviated H2O2. So this is peroxide, right? Peroxide. And a source of base, so hydroxide. Sometimes potassium hydroxide, sometimes sodium hydroxide, it's basically a base. So the second step involves both of these components. And so this is interesting. So the way that this works is that your peroxide is going to get deprotonated to make the peroxy anion, this water. And you will notice that our alkyl borane, and I'm just going to draw one carbon here. I'll put R2 here. This boron has still got an empty orbital, right? So this peroxy anion, actually it's a peroxide, just it's deprotonated. This comes in and attacks. This will attack as we would expect. And this is going to form some black. I'll draw O. R. And I am missing a formal charge, and the formal charge goes, and it's a negative charge because it was negative over here. So where does the negative charge go? On boron, right. Okay, so it's here. Actually, I better draw this the other way. So what happens next is interesting. They call this a migration reaction. Migration. And so the electrons in this bond, they attack the oxygen, and these electrons move on to there. And so after this is done, we end up making our alcohol, and now this boron has got the negative charge is on an electronegative oxygen atom, and so this is like rolling downhill with regard to being on an energy diagram. So instead of having a negative charge on an atom, which isn't electronegative, it's now on oxygen. So, and so the sigma, the electrons in the sigma bond attack the oxygen, and you just break that peroxy. So the OH bond isn't particular. The oxygen bond isn't particularly strong, and so you end up making your alcohol. And this would have to, and if you started with a trialkyl borane, you would the similar reaction would take place on each of these R groups. That would be what's going on there. So when it comes to questions on a test, I don't think I've ever asked for the mechanism of the of this migration, but it's something to keep in mind. So overall, the reaction, if you wanted to do a oh, I forgot to mention something. Okay, we'll have to come back to this in a sec. So the first step would be BH3, and this is done in THF. And so now, right, I totally forgot about that. Okay, so one of the, yeah, okay, so in this step here, the way I drew it, where I formally drew a carbocation, which isn't technically correct, but I was wanting to show why the boron goes onto one carbon and not the other. So there's some really strong evidence that this is a concerted reaction, in the sense that if you are to do this reaction on like a cyclic system like I've drawn, and you isolate the boron intermediate, the BH2 and the H are on the same side. So the BH2 and the H are on the same side when they're added across this double bond. And so in the second step, where you use your peroxide and your hydroxide, the OH, that migration takes place with retention of stereochemistry. So the OH and the H end up being on the same side. So if we were to draw this, I'll try to draw this as a methyl group. So these are the electrons in the, actually, let's just draw them as a, so here's your orbitals, your pi orbitals, here's your pi orbital. So these electrons are going to go attack there, and as it's doing that, this hydrogen is going to go there. So in the course of the reaction, that means that the H is down and the BH2 will be down. So they'll be on the same side. And when it comes to the migration reaction, so for the oxidation, methyl H. And we'll call this R2. When this attacks, it's down. It is still going to end up being down it's not going to go up because there's a proton over here, which we hadn't drawn. So the migration takes place with retention of chemistry. So in the end, when we have our final product, this methyl's up, this proton's up, the OH and the H will be still on the same side. The OH, though, is on the least substituted carbon. So OH goes there, and the proton goes on the more substituted carbon. So that's the hydroboration reaction. So it's completely, it's complementary to the oxymercuration. It's slightly more complex in the sense that we've got this interesting migration step in part 2, but both of them require 2 steps. So in the oxymercuration, the second step is you have to break that carbon-mercury bond. And in the hydroboration reaction, the second step is you're converting a carbon-boron bond to a carbon-oxygen bond. There's one last thing I'll say. I know that we're running out of time, but there's one last thing I'll say is that chemists have developed reagents in which there's only one H on borane, and they've added R groups to it that are really so very large. And so the purpose of this, well, it's twofold. But one of the main purposes is that with those large groups, it really increases the steric factors compared to the electronic factors. So when I was drawing these positive charges on the various carbons, that's an electronic reason why like a delta plus on a more substituted carbon is more stable than a delta plus on a less substituted carbon. But by putting in some really big R groups, like if we had if this is now a really big group and this is a really big group, there's going to be all sorts of steric issues here. Whereas if you've got a really big group on the exterior, these are R groups, there is no steric interaction because this carbon here there is no hindrance there. So that's one of the things which chemists developed, making some very large R groups and even chiral ones, which we could get into in an upper year course. But anyway, so yeah, so I think on Tuesday we'll finish off the addition reactions because we'll talk about a series of things in probably slightly less detail, like mechanistically, but the oxymercuration, that mercurium ions, just like the bromonium ion, and here, this hydroboration reaction, it does the opposite. So the boron and the hydrogen are on the same side, but the oxygen ends up on the least substituted carbon. So that's opposite of what we saw before. Okay, any questions at all? Sorry for running a little bit over time. Okay, well, I'll post this on Top Hat if you want to torture yourself again and watch it. And until then, if you have any questions in the meantime, just fire me off an email. All right?
Thank you.
Super. All right. Have a good day, everybody.